Well, hello and welcome again to our journey into number theory, and we finished last time by proving this result here, that if we have a multiplicative function little f, and if we take the sum of little f over the divisors of n, then and call that function capital F of n, then this capital F of n is also multiplicative. This is a very useful fact because we're going to be dealing with lots of sums of this shape, and we've now shown that sums of this shape are themselves, for each value of n, multiplicative functions. So we're going to use that then to prove the following little result, that the sum of 5d over the divisors of n is just equal to n itself. And that's a nice little example here. So if we add up the values of phi over the divisors, then we get back to the number n itself. So here's the little proof of this. So there's the theorem that we're proving, and we're going to give this a name. I'm going to call that capital F of n, and because phi is a multiplicative function, then so is capital F. And of course the joy of having a multiplicative function is we only need to know what it does to the prime powers. So because capital F is multiplicative, we only need to check the result is true for n equals 1 and for n is a prime power. Now the result's obviously true for n equals 1, so I'm just going to evaluate f at prime powers. So that means I'm taking a sum over the divisors of p to the alpha of 5d, and of course because this is a prime power, the only possible divisors of this are 1p, p squared up to phi to p to the alpha. So I can write down that sum, and of course we have a nice formula for phi of p to the k for any k. So phi of 1 is 1, 5p is p minus 1, 5p squared minus p, and so on all the way up to p to the alpha minus p to the alpha minus 1, and then we look at that series for a second and realize it's a telescoping series, so all of the terms cancel out except for this one. That one survives, and so we get p to the alpha. So that now says that this capital F of p to the alpha is just p to the alpha itself, and that means then because capital F is multiplicative, f of n is just equal to n, i.e. this sum that we started with is just equal to n. So that's a nice little application of the idea of multiplicative functions, and also the fact that if we have a multiplicative function, we just need to see what it does to the prime powers. Now I wanted to introduce now very, very important and very interesting and very pretty new form of multiplication called Dirichlet multiplication. It's a way of combining together multiplicative functions in a way that is in fact very, very useful. Now we're going to be looking at sums of this shape in what's coming up, and that's going to motivate our definition for Dirichlet multiplication, but we define Dirichlet multiplication in the way we're going to because it really works very nicely and gives some very nice results. So just enjoy the shape of this. You've got two functions, two arithmetic functions, not necessarily multiplicative, two arithmetic functions f and g. You sum over the divisors of n. You take f of the divisor and g of the codivisor. So n over d times d is n. So this is a divisor, that's the codivisor. Alternatively, occasionally one looks at sums of this shape, n equals, which is equivalent, n equals d1, d2. You take f of d1 and g of d2. So we're going to then define the Dirichlet product f star g of two arithmetic functions by this formula here. So f star g of n is the sum of the divisors, sum over the divisors of f of the divisor times g of the codivisor. Now the first thing to observe is, which is very trivial to prove, is that this is commutative, because as d runs over the divisors of n, then n over d runs over the divisors but backwards, and so you can simply say this is equal to f of n over d, g of d. So it follows pretty easily that this new multiplication is commutative, Takes a little bit more work to show it is in fact associative, and algebraists will be getting excited at this point because you've got a structure now. If you look at the set of all arithmetic functions, this set now satisfies, under this operation of Dirichlet multiplication, it's commutative and associative. What more can we say? Well, we'll see in a second. Now I'm going to introduce two very simple arithmetic functions. Now the fact that they're very, very simple, do not underestimate these functions. They are very simple, but in fact they're very, very useful. The simplicity of these functions belies their usefulness. The first one is the identity function, which sends everything to 0 except 1. So I of 1 is 1 and I of everything else is 0. And it's called the identity function because, as we'll see, it behaves like an algebraic identity on the set of arithmetic functions with respect to this Dirichlet multiplication. The second one is called the unit function, which is just 1 for all n. So it sends everything to 1. So I'll get these very clear. I of n sends everything to 0 except 1, and u of n sends everything to 1. These functions are trivially completely multiplicative, and now it's an easy exercise to show that if you take f starred with I, or I starred with f, under this new Dirichlet multiplication you get f. That means that this I is behaving like an identity element. So we're getting close to a group structure here. We've got an identity, in fact it's an abelian group, we have associativity, we have closure, inverses we'll have a look at in a moment. Moreover, we can write theorem 3.1 now as mu star I equals the identity, star u, the unit function, is the identity function. And that's simply because this u is just 1, so this is simply saying that the sum of mu over the divisors, remember, was 1 if n is 1 and 0 otherwise, so it's just the identity function. Now again, we're starting to get, if we're thinking algebraically, this is telling me then that these functions are inverses of each other, and indeed the inverse in the group theoretic sense of mu is going to be u, and u inverse is going to be mu. So using these ideas, we can now state and prove a rather lovely relationship between the Dirichlet product and the Mobius function. And this is called the Mobius inversion formula, which turns up in many, many places, not just in number theory. So what it tells us is this: we start off with this, we've got a sum over the divisors of n of this function f, and f only has to be arithmetic, not multiplicative necessarily. And so we have this capital F, we've seen this before, and we know that this capital F is itself, well, if that one's multiplicative, so is this one, but f doesn't have to be multiplicative. This formula now enables us, can we recover this little f from the sum? And the answer is yes, and there it is. We can recover f using the Mobius function. So we can recover f of n by taking a sum over the divisors of mu d times f of the cofactor. Alternatively, we could take a sum over the divisors of f of the divisor times m of the cofactor. And of course, you can see we can write this now using our Dirichlet multiplication star notation. And that's what I'm going to do next, and in fact that will give us the proof of this quite nicely. So the statement then that f is equal to the sum of d divides n of f of d, we can translate that into f is f star u, because remember u is just 1 for any d, u is just 1. And so I can simply put a 1 in here and think of that as the sum of, or rather think of that as u of n over d, and so I can write f like that. And now what I want to do is I'm going to take a Dirichlet product of both sides of this with mu. So I get this, so it's f star u star mu And of course this operation is associative, so I can move the brackets to here, and we've just seen that u star mu is the identity function. And if you star the identity with any f, you get f. And now we just translate all that back into sigma notation, and we have f of n then is f star mu of n, and that's just equal to mu star f of n, and I can write that now using our writing down what this star means. We take a sum over the divisors of mu and f. Mu at d and f at the co-divisor. So that follows instantly from just using this Dirichlet multiplication. We can now apply this to this Mobius inversion formula, and we can get a nice formula for 5n, connecting it with the Mobius function. So all we do is we apply Mobius inversion. We've proven this result before, that the sum of 5d over the divisors is equal to n. And all we need to do now is just apply this Mobius inversion. So I can recover 5n by taking the sum of mu of d times n over d, and I can just take the n out the front, and we get this nice result here. It connects 5n and mu. Now indeed we'll see that this mu, which remember came from the zeta function, the zeta function is intimately connected with almost all of the important arithmetic functions. And so it's not quite surprising here that it's the reciprocal of zeta, which is the mu function, is connected in this way with phi. There are lots of other connections we'll see later. Now, from an algebraic perspective, we've seen that this Dirichlet multiplication is commutative, associative, there's an identity. So if I take the set of all arithmetic functions, we've almost got a group. We just need to have some concept of inverse, some algebraic inverse. And we saw above that when we take a Dirichlet product of mu and u, we get the identity. And so I can interpret that as saying that these two are inverse functions of each other with respect to this new Dirichlet multiplication. Well, the obvious question is it true that any arithmetic function has an inverse, which is also arithmetic, such that when I compose f with its inverse under this Dirichlet product, then I get the identity? And the answer is, well, yes, almost all of the time. You just require f of 1 not to be 0. Now, it's left really as a tutorial exercise to fiddle around with this and show this works. This formula here is giving me a recursive way of constructing and defining the inverse function to a given arithmetic function. It says we firstly have to define f inverse of 1, I define to be 1 over f of 1. And then recursively, f inverse of n is minus 1 on f of 1. You see why we want that not to be 0. We take a sum over the divisors, but the Dirichlet divisors, the divisors of d strictly less than n. F inverse of d and f of the cofactor. And this gives me, starting off with this gives me a recursive way of evaluating this new function f inverse. And you can prove by induction that if you compose f with this f inverse, that is with this, you actually do in fact get the identity. And I'll leave you to have a fiddle with that. You can do that by induction. If you've got a completely multiplicative function, then f inverse, it turns out to be just mu times f of n, for n bigger than 1. Now, the proof of this is fairly easy. We just let g be mu times f, which is what this is here. And then if I then compose g with f under Dirichlet multiplication, then that means I take mu d f d, and then I'm going to take f of the cofactor. So I take my g, which is this one here, and then I compose that with f, so I get f of the cofactor. And if it's completely multiplicative, then f of d times f of n over d is just f of n times sum over the divisors of mu of d. And of course, this thing here is 0 unless n is 1, in which case it's 1. And because it's completely multiplicative, f of 1 is 1, and so I just get the identity. And so that means this g, this mu of f, is in fact the inverse of f. One can also show that the f star g inverse is f inverse star g inverse whenever the inverses exist. Well, I'm going to introduce yet another of these arithmetic functions, and this one is an example of a completely multiplicative function, and this is a capital N of n, and sends every number exactly to itself. So keep in mind the three different special functions we've had. We've had the identity, which sends everything to 0 except 1, which goes to 1. We've had the unit function, which sends everything to 1, and this capital N function, which sends n exactly to itself. Now, it's clear then that n inverse, because n is completely multiplicative by what we did up here, n inverse is just mu times capital N. And also we've seen that mu inverse is u, as we've seen before. Now, it'd be nice to get a formula for phi inverse to see can we calculate that. We don't want to do it using the recursive definition. That you rarely use this to actually calculate the inverse. Sometimes you have to if it's a new function you don't know much about, but most of the time we're going to try and get the inverses of our arithmetic functions using some of the theorems that we've got. So I want to get a nice formula for phi inverse. Now, we've proven above that phi of n, that was theorem 3.6, is n times sum over the divisors mu of d on d. And I can write this now in terms of our capital N function by saying phi then is mu star capital N. So, to get the inverse of phi, we're going to take mu star n inverse. Now, that's going to be just mu inverse n inverse, which is mu inverse. Now, n inverse we saw was mu times n because n is completely multiplicative. And we've seen that the inverse of mu is u. And so this becomes u star mu n. I just turn this around, it's commutative. And that tells me then that phi inverse of n is going to be this Dirichlet product, which is simply this. So it's mu d n d times u of the cofactor. Now u, remember, is just the unit, so it sends everything to 1, so that's just 1. And n of d is just d, so this sum collapses down to d times mu d, summing over the divisors. Now this phi inverse is multiplicative, and so we only need to evaluate phi inverse at prime powers. So we can do that. We evaluate phi inverse at p to the alpha, so we take a sum over the divisors of p to the alpha d mu of d. Well, there are not too many of them because that are not going to give me 0 here. If I put d as 1, I get 1 times mu of 1. If I put d as p, I get p times mu of p. And after that, d will be a power of p, so it contains a square, and so mu of d is 0. So all the rest of the terms in the sum are 0, and this is 1 minus p. So this tells me what phi inverse does to a power of a prime. It sends it to 1 minus that prime, and then I can use the fact that it's multiplicative to say phi inverse of n then is a product over all the primes dividing n 1 minus p. And that gives me a very nice little formula for phi inverse of n. I made up just a little table here just to summarise what we've had, plus some other little ones here you can experiment with. If f is the identity is its own inverse, as you might expect. We've seen that the inverse of u is mu, and then the inverse of mu is u, obviously. We've seen the inverse of capital N is n times mu. We've just proven that the inverse of phi is u star mu n, which we did in our earlier example there. These ones we haven't done, but you might like to experiment with these and show these ones. The inverse of tor, the inverse of the number of divisors, turns out to be just mu star mu, and the inverse of sigma is mu n star mu. And so again, you can see that this mu, this Mobius function, is just playing such an important role in this context of arithmetic functions. And by the way, of course, also we've seen that because we now have an inverse, we can now see that the set of all arithmetic functions, so coming back to what we had here, the set of all arithmetic functions, f, as long as f of 1 is not 0, then the set of all such arithmetic functions will form an abelian group under this Dirichlet product. So from an algebraic point of view, this is also a very interesting multiplication and an interesting structure. And we'll continue on with this in the next section.